Hi everyone, and welcome to a new video about inverse Laplace transform, and we continue with the system with the complex roots. So what we have is the following situation. We would like to calculate the inverse Laplace transform of y of s, which is given by this transfer function. What you see in this transfer function is that there is a first order term and a second order term in the denominator, which makes this system a third order system. In addition, we have also a zero, which is shown here in the numerator. So this system is a little bit complicated than the previous example where we had a pure second order system with only complex roots. Now, how do we start in this situation? What is actually the way to tackle this? Now, since we have a pure real pole here, and these two poles, which can be a complex, repeated, or maybe complex, we can use again here partial fraction expansion. We can also try to do this as in the previous example using completing the squares, but let's do this in the example also with partial fraction expansion, where you see the situation also for a third order system and a complex with a complex poles. So let's continue. So we have the system, and I have rewritten this in the numerator, as you can see here, so that you can see the zero directly. It will help us in analysis. Now, if I move on, what I do is partial fraction expansion, and then I get the following expression. This will be placed in the first fraction, which is a divided by s plus 4, plus bs plus c, which is now, we have now two unknowns in the numerator in the second term, divided by the second order term. So as you can see, the first order term of this denominator we will taking here with a coefficient, unknown coefficient a, and in the second part of the fraction I will take bs plus c, which are the two other unknowns for the second order term. So what we have to do now is, again, making the denominators equal to each other. So in the next step, I will multiply the numerator and the denominator for each part here, such that the denominators are equal to each other for the left side and the right side. So the following step will illustrate that. So what I have done for the first term on the right side, shown here in red, I multiply the numerator and denominator of this one with s squared plus 6s plus 34, and this one I just multiply by s plus 4, so I get exactly the same denominator as the transfer function in the original form. Now, since the denominators of the left side and the denominator of the right side terms are exactly equal to each other, I can say mathematically that the numerators must be equal to each other. So I can say this numerator is equal to the numerator here for the first term plus the numerator for the second term. So that's actually what we get for the next step. So next steps are take that and equate it to each other. We have now three unknowns, a, b, and c. Now, we can do this again as we did in the previous videos. We can select a convenient value for s, such that only one unknown is left in our equation. If I look at this equation, I can say that if I select s is equal to minus 4, this will be gone, so I lose b and c, so I'm only left with a. So that's actually what I do first. So I will say set s equal to minus 4, then I have the following. If I substitute the values for s, so s is minus 4 for the left side and s is minus 4 for the right side. So this will be a value, just a number. This is gone. It doesn't matter what this is inside, but this will result in 0. So I have now, in total, on the left side, I have here minus 2 times a will be minus 16. This will be in total 26. Times a will be 26a plus 0. And I will now have the value of a. That's actually the value for the coefficient a. We can continue again by selecting a convenient value for s to determine the other unknowns, other coefficients. So since I know a, I can use that in the next steps. So I can say, if I now want to get rid of b, that is possible by selecting s is equal to 0. So if I do that, and then substitute value for s is equal to 0, and use this a, which I already calculated in the first step. So let's do that here. As you can see, s is equal to 0. This will be 16 on the left side, and I have now substituted the value of a, and s is equal to 0. And here is s is also equal to 0, and I am losing the b. So I'm only left with the parameter of the coefficient, I'm say, of c. So if I now simplify this expression, I get the following situation. So 16 is equal to minus 272 divided by 13 plus 4c. So if you do the math here, you will get for c is equal to 120 divided by 13. So we have the a and we have the c. So we are only left with b. So how can we do that? Again, you can choose a convenient value for calculating your unknown parameter b. Since we know the a and also the c, it doesn't matter which value you take for s in the next step. Of course, it is not really handy to take or to select a very difficult value for s, so let's take just 1. You can also take -1 or 2, it doesn't matter, but I think 1 will do the job. So if I now set 1 and I use the values of a and c also in this equation, I get the following situation. So I have now substituted the value of s and also inserted the values of a and also c, as you can see here. Now the b is now the only unknown in this equation. So if I do the math here, just simplify this stuff here, I get 24 is equal to minus 328 divided by 13 plus, and then b is just as b, plus 120 divided by 13 times 5. Now, I just do the math here, just simplify. It is not really that difficult, I think. You will get that b is equal to 8 divided by 13. Okay, that's actually for this part. So we have now the a, we have the b, and we have the c. So I can now just substitute those values, those three values, in here, and then continue. So what we have is the following situation for our transfer function with two terms. So we have a first term, which is quite easy to determine the inverse Laplace transform of this one, but this term we have to work on it. So we have to do some additional steps to find the inverse Laplace transform of that one. So if I now a little bit simplify this, I can say get the 8 over 13 outside, so as a coefficient or as a parameter, I will get the following simplified form. Why is this better to work with instead of this one? I can now see directly what is now the 0, and also will be helpful when I want to calculate the inverse Laplace transform for this part. That will be clear when we go to the next step. So again, this is 15. Why? Because if I do 15 times 8, it will be 120. 120 divided by 13 is exact same as we have here. And 8 times 8 over 13 is multiplied by s. And I get exact the same form. And I have now placed also this term in front of this expression. So let's move on and look actually just for the situation how to determine now the inverse Laplace transform of this one. So if I now zoom in this part, because that part is quite easy and we can do that straight quite easily, but this one will take some time, so let's carry out some steps to tackle it also. So if I now just focus on that one, I can use here completing squares as we did in the previous example. That results in the following. Why? Because I divide by the 2, so I do 6 divided by 2, and I square that, so I do s plus 3 divide that one, completely quantity squared. And if I look at this, I just work this out, I get s squared plus 6s plus 9. But I have that 34 as a constant here. So to get at 34, I need additional 25. We have done this in the previous video. I think this is doable for you guys. Now, if I continue, just to look at this situation, I can write it also like this. So I've just changed 25 in 5 squared. You will see why I do this shortly. I can, in addition, change the numerator here in this form. So I have now just made this 15, a summation of 3 and 12. Why I do that is the following, because I have now s plus 3 squared, and I have also here s plus c squared. I need an additional term, which will be again clear shortly, like a 3 here. So if I just adjust this, so write that in a different form, I have also a 3 here in the denominator and also numerator. If I now split this, I get the following. What you can see is here now we have an s plus 3 and an s plus 3 in the numerator and the denominator also, and we have now here 5 squared again. And this one is just 12, so I have to also adjust that. This is due to the Laplace transform actually, which is shown here on the right side. So all those steps I have now carried out here is due to the entries 8 and 9, which I can use from the Laplace transform table. If I look at this, for example, this is actually entry 9. The a here is 3, and the omega, which is shown here, is 5. But if I look at entry 8, which is this part, I can now also pinpoint which is now the a, but I'm not able to make this directly omega in the numerator. So if I now just make an additional, so this is just the entry 8 and this is the entry 9. If I now make the adjustment here, so just make a simplification, so just you can see, okay, this 12 over 5 will be placed here as the constant, and this 5 is now the omega for the entry 8. So as you can see, we have now directly what is now the omega, what is now the a for this second term also. The first term is now clear using entry 9, and the second term is also doable using the entry 8. And this is just a factor, so you can just place it in front and multiply the result. So what we have is, again, this will result in the entry 9 and this will result in entry 8. So what we have is the situation for our transfer function as follows. So the first term here, we just copy that, we haven't done anything with it. But the second term here with the multiplication factor 8 over 13, will you just take it over, copy that. But this one is now written in 2 terms, and that one is placed here in a form conveniently such that we can directly determine our inverse Laplace transform for each term. So the next step is step by step and term by term determining the inverse Laplace transform. If I look at this one, it's just again entry 6, which is just a very familiar transformation. So I get 1 over s plus a, which is here, the a is here 4, and I get e to the power minus 4t. That's just very simple. For that one, I get the entry 9, that will be e to the power minus 3t times the cosine of 5t. And for the third one, this one is entry 8, and that will result in e to the power minus 3t times the sine of the omega t, which is sine of 5t. So I have now collected all the necessary elements for our transfer function, for the inverse, of course, inverse Laplace transform of our transfer function. So if I now collect them together, then the inverse Laplace transform will be y of t will be minus 8 over 13 times e to the power minus 4t, which is shown here, plus 8 over 13 times, in brackets, these two values, of course, together added, and this one is multiplied also by 12 over 5, which is, of course, the necessary coefficient for the second term. Now, If I just a little bit simplify this, I can get rid of this e to the power minus 3t and place it outside, so it will be much more readable. So that's just simplification. For the next step, we get the following. So I just place it outside. This will be cosine 5t, and this will be 12 over 5 times the sine of 5t. And that's actually in this final form. You can, of course, continue simplifying this, because I see 8 over 13 here and also 8 over 13 here, but this is, for now, I think, good enough. This is actually the final step, and as you can see, we have carried out several various steps to find the inverse Laplace transform for this function. Since we have a third order system and also complex roots, because I haven't calculated the roots in this video, I've done this in the previous video with a pure second order system with complex roots, but this system has also complex roots. You can do that by yourself by equating this part equal to 0, you will get complex roots. So we have again used partial fraction expansion and have done that by selecting the values, convenient values for s. This is just a way to work out the inverse Laplace transform. There are other ways, like a residue theorem and other methods. So if you are familiar with that one, that's also fine. My way of working out these examples is the following. So if you have another option, please do that. No problem at all. Okay guys, this is for this example, a little bit challenging compared to the previous examples I have also discussed with you guys. If you have questions, please let me know and we keep in touch. Take care.